In this video, we're going to graph polar equations and convert back and forth between polar and Cartesian equations using the same identities introduced in TR-45. On a Cartesian coordinate system, this line is the graph of y equals 2, a horizontal line 2 units along the y-axis. And this line is the graph of x equals 1, a vertical line 1 unit along the x-axis. These are the simplest xy Cartesian equations where one coordinate is a constant and the other can be anything. We can do the same thing with polar coordinates. When we let r be a constant, we get the simple equation r equals 3. On a graph, this is the set of all points whose distance from the pole is 3 and whose theta coordinate can be anything. This is a circle centered on the pole whose radius is 3. Finally, we can let theta be a constant, like theta equals 25 degrees. This equation is represented by the set of all points whose polar angle is 25 degrees and whose r-coordinate can be anything, positive or negative. So theta equals 25 degrees is a line through the pole at an angle of 25 degrees. Cartesian equations usually have the form y equals some function of x, meaning y is the dependent variable and x is the independent variable. The value for y depends on the value for x. Polar equations have the format r equals some function of theta, meaning r is the dependent variable and theta is the independent variable. R depends on theta. Interestingly, Cartesian coordinate pairs list independent first and then dependent, but polar coordinate pairs list dependent first and then independent. I can't say I know why this is. I'm just an engineer. Maybe a mathematician can tell us in the comments. So we've plotted the simplest possible polar equations, those where one variable, r or theta, is a constant. Now let's plot some more interesting polar equations. When you first learned to graph xy equations on a Cartesian coordinate system, you may have made a t-chart like this, where you would list different values for the independent variable x, and then calculate the dependent y value corresponding to each x. The resulting ordered pairs could be plotted to denote points on the equation's graph. We can do the same thing with an equation in polar form. We list different values for the independent variable theta, then, using the function we're intending to graph, calculate the value of r, the dependent variable, corresponding to each value of theta. Since our independent variable is an angle, let's plot a trig function of angle theta. R equals sine theta. That's a common function when learning polar equations, and it's interesting too. Note that this is significantly different than our first two sample polar equations, r equals 3 and theta equals 25 degrees. In neither case did r depend on theta. But now, with r equals sine theta, r will change as theta changes. We know sine theta won't ever be bigger than 1, so we can scale our polar coordinate system so that the largest circle has a radius 1 with smaller circles inside. I've used degrees for this chart and listed out multiples of 15 degrees from 0 to 180. That'll give us a lot of points to plot. We'll get to the reflex angles from 180 to 360 degrees next. I'll write the sine of each angle to 2 decimal places. I can't plot more precisely than that by eye. See TR-16 for evaluating trig functions on a calculator. The first angle to plot is 0. R equals sine 0, which is 0. So the first point is theta equals 0, r equals 0. Anytime r is 0, the distance from the pole is 0. So the point is on the pole, and we'll plot a point here. When theta equals 15 degrees, r is about 0.26, so here. Sine 30 degrees is our small number, 0.5, so here. At 45 degrees, r is medium, square root of 2 over 2, about 0.71, here. Working all the way to 180 degrees yields these points, which form a circle on the polar coordinate system. How interesting! The polar equation r equals sine theta is a circle on the polar coordinate system. For reflex angles in quadrants 3 and 4, the angle points down here, but since sine is negative, the value for r gets backed up into quadrants 1 and 2. At 210 degrees, this direction, r is negative, so the plot is at this point again. As theta goes around the big circle once, the plotted circle is traced twice. In the last video, we learned how to convert point coordinates from one system to the other. Another skill we're expected to learn in trig class is to convert equations from one system to the other. We'll need these same identities that you can either memorize or derive quickly from the diagram. We'll start with the four simplest equations we've already mentioned. The first equation is y equals 2. Here's its graph, a horizontal line. What polar equation corresponds to the same line? Well, y equals r sine theta, so let's substitute r sine theta for y. That's r sine theta equals 2. We want to isolate r to get r equals some function of theta. So let's divide both sides by sine theta to get r equals 2 over sine theta. That's probably okay with your instructor, but since 1 over sine theta equals cosecant theta, we can also write r equals 2 cosecant theta. Let's try it out with a few points on the polar coordinate system. When theta equals pi over 2, it's a right angle. Sine is 1, so its reciprocal, cosecant, is 1. 2 times 1 is 2, so we plot a point here at 2, pi over 2. At pi over 3 and 2 pi over 3, sine is large, square root of 3 over 2. So cosecant, its reciprocal, is 2 over square root of 3, about 1.15. And 2 times about 1.15 is about 2.3, these points. When theta equals pi over 4 and 3 pi over 4, sine is square root of 2 over 2. Cosecant, then, is 2 over square root of 2, which is about 1.41. So 2 times cosecant is about 2.82, these points. And when theta equals pi over 6 and 5 pi over 6, sine is 1/2. Its reciprocal is 2, so 2 times cosecant is 4, here. So the Cartesian equation and polar equation describe the same line. Let's go on to the next equation, x equals 1, which is a vertical line. To convert x equals 1 to a polar equation, we note that x equals r cosine theta. So r cosine theta equals 1. To isolate r, divide through by cosine. R equals 1 over cosine, or r equals secant theta. Same line. Pretty simple. Just use the identities to make substitutions to convert from one system to the other. Now let's convert the simple polar equations to Cartesian. First is r equals 3, a circle. Our identity tells us that r equals square root of x squared plus y squared. So, plugging in, we get square root of x squared plus y squared equals 3. Let's square both sides to get rid of the radical. We could stop right here because this is the format for the equation of a circle. I'll come back to this in a second, but first let me quickly solve for y in terms of x. Subtract x squared from both sides and take the square root to get y equals plus or minus square root of 9 minus x squared. Either of these formats is correct and will be acceptable to your instructor, but the first format gives us the opportunity to quickly review the general equation of a circle, because we'll need it in a few minutes. This should be analytical geometry review, so I'll be brief. The general equation for a circle is x minus x center squared plus y minus y center squared equals radius squared. The center of the circle can be anywhere in the plane by specifying coordinate values of x center and y center. For example, the graph of the equation x minus 3 squared plus y plus 2 squared equals 16 is a circle whose radius is 4, the square root of 16, and whose center is at 3, -2. Note that the sign flips for the center's coordinates, -3 and +2, but the center at +3, -2. So the equation x squared plus y squared equals r squared is the special case where both offsets are 0, so the circle has a radius r and is centered at 0, 0, the origin. The last simple equation to convert is theta equals 25 degrees. Our identity says theta equals arctangent y over x, so let's write 25 degrees equals arctangent y over x. This is the same as tangent 25 degrees equals y over x, by taking the tangent of both sides, if you will. To isolate y and get y in terms of x, we multiply both sides by x and flip the equation around to get y equals tangent 25 degrees times x. Our calculator will tell us that tangent 25 degrees is about 0.466, so the Cartesian equation of the line is y equals 0.466x. So we've covered converting the four simplest equations back and forth. Now let's convert that more interesting polar equation, r equals sine theta. Fair warning, the first four sample equations all converted simply. As a rule, converting Cartesian to polar equations is pretty easy, but converting polar to Cartesian equations can require a good bit of algebra, so don't forget your algebra. We start with r equals sine theta. Let's look at our identities to find some substitutions. The variables in the equation are r and theta. We want to convert them into x and y. Well, we have an identity with r sine theta, which almost matches what we have, sine theta. So let's multiply both sides of our equation by r to get a match. R squared equals r sine theta. On the right-hand side, r sine theta equals y. So let's write that. And on the left-hand side, well, we have r equals square root of x squared plus y squared, so r squared would be x squared plus y squared without the square root. The equation becomes x squared plus y squared equals y. If we entered this equation into a graphing calculator or app, we'd get the circle as we expect. But let's exert a little more effort and get this equation into the general form for a circle. We won't need the identities for this problem anymore, so let me clear them out and write a reminder of the general Cartesian form of a circle. Let's get the xy variables on one side of the equal sign by subtracting y from both sides. The x squared term is fine as it is. We can just rewrite it as x minus 0 squared to match this part of the general form. But the y part of the equations don't match. This is where algebra comes in. I warned you there could be a lot of algebra in these conversions. We can write the y expression as a quadratic equation, y squared minus y plus 0 equals 0. And we want to transform it into a form that looks like this. A squared binomial, y minus some constant v, quantity squared, equals some constant k, to match the right part of the general circle equation. From algebra, you may remember a technique for solving quadratic equations called completing the square. I'm not going to go over the technique in detail since it should be a review, but I've linked to a good video in the description. So when we complete the square, the quadratic equation y squared minus y plus 0 equals 0 can be expressed as the equivalent equation y minus 1/2 squared equals 1/4. Same equation, but in a different format, the format that matches the general equation of a circle. Let me expand y minus 1/2 squared to show you they're the same. The first terms are y times y, so y squared. The outer terms are y and negative 1/2, so negative 1/2 y. The inner terms are negative 1/2 and y, so another negative 1/2 y. And the last terms are both negative 1/2, so negative 1/2 squared is positive 1/4. And the whole expression equals 1/4, so when we subtract 1/4 from both sides, we get our original quadratic equation. Usually, completing the square is used to solve quadratic equations, but in this case, we've just used the technique to change the format of the equation to match the general Cartesian form of a circle. Our converted equation can now be written as x minus 0 squared plus y minus 1/2 squared equals 1/4. This almost matches the general form for the equation of a circle. We just need to express the right-hand side as a square. Since 1/4 equals 1/2 squared, our equation becomes x minus 0 squared plus y minus 1/2 squared equals 1/2 squared. This is a circle whose center is at 0, 1/2, and whose radius is 1/2, which exactly corresponds to the circle r equals sine theta. Let's convert another Cartesian equation to polar, a straight line in the form y equals mx plus b, where m is the slope and b is the y-intercept. Remember, m and b are constants, not variables. X equals r cosine theta and y equals r sine theta. We want to isolate r to have r equal some function of theta. So let's subtract n times r cosine theta from both sides. Factor out the r, then divide both sides by sine theta minus m cosine theta to get r in terms of theta, b over sine theta minus m cosine theta. This will work fine unless b is 0. If b, the y-intercept, were 0, then the equation will yield r equals 0 for all theta, and r equals 0 is just a point at the pole, not a line, so that's not right. When there's no y-intercept, we have y equals mx, which passes through the origin. Isolating m, we get m equals y over x, which is also equal to tangent theta. Since tangent theta equals m, theta equals arctangent m. This plots as a straight line whose slope is m. Let's convert another Cartesian equation to polar, y equals x squared, which you should recognize as a parabola. Substituting y equals r sine theta and x equals r cosine theta, we get r sine theta equals r squared cosine squared theta. Let's cancel through an r, then isolate the r that remains by dividing both sides by cosine squared to get r equals sine theta over cosine squared theta, which is fine, but let's expand this out and substitute to get r equals tan theta times secant theta. So we've converted points and equations back and forth between coordinate systems. You'll find that converting coordinates is always easy. Cartesian to polar or polar to Cartesian. Very easy to convert points. For converting equations, you'll find that Cartesian to polar is easy. Plug in x and y and then simplify. But converting polar to Cartesian equations is not always easy. Without going through its details, I'm going to show a conversion of r equals 2 sine 3 theta to Cartesian form with yellow annotations for each step. Pause if you're interested in following the logic on your own. This conversion features two identities, the angle sum and double angle identities, plus lots of factoring and simplifying. In short, we're trying to get a bunch of r cosine theta and r sine theta terms that we can substitute with x and y. It's possible, but not likely, that you'll be given a problem this complicated in a first-year trig class in high school or college. There are two more things I want to show you, and I'll use the first to show you the second. You should become familiar with the free online graphing calculator called Desmos. It's at desmos.com/calculator. Here's what it looks like. Enter an equation here, get its graph, y equals 2x squared. We can switch to a polar coordinate system by clicking the wrench icon at the upper right. Here's where to choose between Cartesian and polar coordinates. Let's type in a new equation. The polar equation we used, r equals sine theta. We get the circle we plotted earlier. To enter the variable theta, just type THET and when you type the A, it will convert into the theta symbol. Pretty neat. To plot a polar equation, you must use lowercase r as your variable. If you use a capital R or some other variable, Desmos will assume you intend to plot a Cartesian equation, like this, and we get the sine wave plot. The Cartesian and polar coordinate grids are optional overlays, and just for reference, they don't determine the type of plot, your variable names do. Lowercase y equals will get a Cartesian plot, even if the coordinate grid is polar, and lowercase r equals will get a polar plot, even if the coordinate grid is Cartesian. You can use Desmos to check your work. I confess that while preparing the videos on trig proofs, I used Desmos to graph the left-hand side and right-hand side to be sure their graphs matched and that I hadn't made a mistake while preparing the problems. The second thing I wanted to show using Desmos is the series of flower-looking graphs that result from trig functions of multiples of theta. Let's use Desmos to graph that complicated conversion example, r equals 2 sine 3 theta. Remember to use lowercase r. The graph looks like a flower with 3 petals. When you graph polar equations like these by hand, like on a test or homework, create a T-chart and start with a column for theta. Then add columns to build the expression one element at a time. So to plot 2 sine 3 theta, start with theta. Then create a column for 3 theta, then add a column for sine 3 theta, and finally a column for 2 sine 3 theta. The polar coordinates are the ordered pairs consisting of the first and last columns. This avoids the confusion of trying to do everything in one step and makes it easier to find errors. As a double check, let's put our resulting Cartesian equation into Desmos. If we didn't make a mistake, we get the same plot. Here, the red equation is plotted directly over the black equation. Same. Desmos is a wonderful, free tool, and you can use it for math courses besides trigonometry. The website desmos.com has learning resources, and in the description below, I've linked to their YouTube playlist, which has about 40 very short videos showing how to use the tool. Highly recommended, and learning it could be a good investment in your academic or professional life. Let me show you a few more plots. I'll put cosine and sine on the same graph. Here's 2 theta. Each flower has 4 petals. Here's 3 theta. Each flower has 3 petals. 4 theta, 8 petals. 5 theta, 5 petals. If we consider the argument to be n theta, then when n is odd, we get n petals, and when n is even, we get 2n petals. The reason has to do with negative r values. They either retrace a previously drawn petal, or they draw a new petal. So all of the flowers with an odd number of petals are drawn twice, so there's half as many. And the even-numbered flowers are all drawn once without repeating. I'll link to another nice video that shows even more beautiful patterns in more detail. See the description for The Art of Polar Graphs. We finally reached the end of this trigonometry video series. I hope you found it helpful. If so, will you please share it with your friends and colleagues? I'll post more educational videos, so please subscribe if you'd like to know when they're posted. I'm Dennis Davis. Thanks for watching, be well, and good luck with your studies.